Professor Pelton. This is Trigonometry, Chapter 3, Section 4. This is Part 2 of 3. So the next thing we're going to cover is the unit vectors. This is the way you write the vectors in terms of an equation, because we need vectors as equations to be able to do calculations. So a picture is not going to help us, only for visual and understanding. So typically you're going to write vectors in trig as some value I plus some value j. When you get to physics class, you'll need a three-dimensional vector, so you do a k variable there. So ijk, an italic ijk, basically. So that gives you your x, y, and z's, but we're not going to need the z. We're going to do two-dimensionals, so we only want an x component and a y component. For 2D, vectors in trig, which will be mostly bearings of forces and velocities and a few other things like that. Okay. Okay, so again, our vectors are in the second dimension only. We're not doing the third dimension. So there's the magnitude formula changes slightly because now we don't have two coordinates. We just use the a and b values from the vector. So if I'm going to graph this vector, I just go to -3, 4, and I put a point, and I draw the vector to that point. So now I want the magnitude of that vector. So if I do that, the magnitude of the vector equals the square root of -3 squared plus 4 squared. So that gives me the square root of 9 plus 16. So that gives me 25, which is 5. So that vector is in fact 5 long. Okay, so using the vector equation, okay, it's called the unit vector, not called the unit vector, sorry, we're using the units with vectors. Draw the vector and figure out the magnitude of the vector, which is the length. Pause the video. Okay, so this vector is 3, -3. So 3, -3 puts me right here. Alright, so that point is 3, -3. So we want to know the magnitude now. So let's see here. The magnitude is going to be 3 squared plus -3 squared. So that's 9 plus 9 is root 18, which is 2 times 3 times 3. So that's 3 root 2. Root 2, sorry. So that is 3 root 2. Okay, so that's the basic components of a vector. But here's the problem. All of those vectors are starting from an origin 0, 0. So if we were going to do longitude and latitude, we were to take a plane from Dallas to Chicago, or Chicago to Atlanta, or something like that, none of those start at 0, 0. Right? They start at some location to some location, from point A to point B, or point B to point A, whatever the case may be. So not everything is, of course, airplanes, but you get the idea of locations. Locations are not necessarily starting from some kind of 0, 0 origin. If all planes started at the origin, they'd be off the coast of Africa, which is where the center of the longitude-latitude system is. So we need to take the original coordinates and make a standard position vector, because from the standard position vector we can make an equation. And we need all vectors as equations, because there is no equation here, right? There is no equation for that vector there. So that gives us a big crying Pelton, right? So we need an equation. Okay? So it must be starting from 0, 0 to do that. So we need to use this formula here, which is another component of the distance formula, basically. But in the past, it didn't matter whether it was 2 or 1 or 1 or 2 in the order, but now it does matter. It has to be 2 first, 1 second. So basically it has to be terminal minus initial. The other way around is the wrong answer. So let's do the next problem correctly and incorrectly. Alright, so I'm going to write two things on here. Incorrect and correct. So we know the vector has to be the distance formula. Well, partially. I plus j, and then I plus j. Okay, so let's say we do it incorrectly, and we did initial minus terminal for this original vector that we had, xy, xy. Okay, so if I did that, that would be 3 minus negative 2, and negative 1 minus the 5. So that would give me a vector of 5i minus 6j. But if I did 5i minus 6j, that would put me over here at 5, negative 6. Well, that can't be true. So this can't be true. That gave me the vector going in the opposite direction, right? That can't be true. So if I did it the correct way, which is terminal minus initial, right? So this is my terminal, and that's my initial according to the directions. So if I do that, it'll give me negative 2 minus 3 and 5 minus negative 1, which will give me the correct vector of negative 5i plus 6j. And that gives me the actual standard position vector, which is what we actually want. Okay, pause the video, try the student problem. Okay, so you should first draw the coordinates, so negative 1, 3, and 5, 2. So that is initial and the terminal. So the new one comes from there and goes to the new position. So that vector equation is going to be I plus j, so terminal minus initial, and that gives us a vector of 6i minus 1j. So 6 minus 1, 1, 2, 3, 4, 5, 6, negative 1 is right there. So that is the standard position vector and its equation. Okay? Alright, next piece. I'm going to do some calculations using this. Okay, so here what this is saying is when you add subtract vectors, you have to add the common variables, just like you can't add x's with y's or y's with x's. It has to be x's, x's, y's with y's in algebra, and same here, i's with i's and j's with j's. So if I take my two vectors here and add them together, v plus w, I'm going to get 5i plus 4j plus 6i minus 9j for a final answer of 11i plus 5j as my v plus w. Okay, likewise, parentheses don't make a difference in the first one, however they do make a difference here, because if I do this one, 5i plus 4j minus 6i minus 9j, that will not give me the right answer because it's minus the entire w. So in fact, I have negative 1i, and the double negative makes a negative there, right? Or a positive, rather. Makes a negative on the first one. So that gives me a 13j. Okay, so the next one is a scalar, so you just multiply everything by 6. So this is really 6 times 5i plus 4j. Or in other words, 30i plus 24j. And then a negative just makes it go the opposite direction, so that's negative 3 times 5i plus 4j. So negative 15i minus 12j. Okay, we'll try the last one, which is a scalar and a subtraction. So we try this one. It's 4 times the vector minus 2 times the vector. So that's 20i plus 16j minus 12i plus 18j. Oof, this is messing up pretty bad. Okay, so we combine the like terms. We get 20 minus 12 is 8i. 16 plus 18 is 34j. Okay, pause the video and try these student problems. Okay, so the student problems, we have 7i plus 3j plus 4i minus 5j for a final answer of 11i minus 2j. So parentheses were not necessarily there, however the subtraction will be. So that's 7i plus 3j minus 4i minus 5j. So that's going to give me 3i after you minus the 4, and minus, let's see, negative negative give me a positive 5, so that's 8j is the final answer there. Okay, and then the next one is a scalar. So that's 8 times the vector. So that's 56i plus 24j. And then negative 5 times the vector. So 7i plus 3j. So that's going to give me negative 35i plus 15j. This next one's a difference and a scalar. So that's 6 times the 7i plus 3j. Minus 3 times 4i minus 5j. So that gives me 42i plus 18j minus 12i plus 15j. For a final answer, 42 minus 12 is 30i. And let's see, 18 and 15 gives me 33j. Okay. All right, next page. So the next thing just shows you all the various properties that work for this. Of course, the only thing that doesn't work that we talked about before is v minus w is not the same as w minus v. So the commutative property does not work for addition. It does work for addition, but not subtraction of these, because you get the opposite vector. And what's important here, what's different, is the bold 0 and the non-bold 0 mean two different things. The bold 0 stands for the 0 vector, whereas a non-bold 0 just stands for the number 0. Okay? So the 0 vector is important because it gives us a direction, usually no direction and no magnitude, versus a unit vector. Because a vector of magnitude 1 will give us a direction with only a multiple of 1, which is very handy for doing calculations, because multiply by 1 doesn't change anything. So that's the thing we want to do now, is a unit vector. Because a 0 vector is just 0, so that's pretty straightforward. There's nothing to do with that, per se. Okay, so if I take any vector and divide it by its length, it becomes 1. Because if the length is 50 long, I divide by 50, I get 1. If the vector is 13 long, I divide by 13, it's still 1. So I take the magnitude. So that's 5 squared plus negative 12 squared, coming from the vector. Oops. I get 25 plus 144, which is 169, which is 13. So if I want the unit vector, I got to use the formula, which is the vector divided by its length, which is the magnitude. So this vector is 5i minus 12j. So I divide that by 13. I get 5/13 I minus 12/13 j. So that is a magnitude in the same direction, but the length is only 1. So if it's a force of 1. It's a velocity, it's a velocity of 1, whatever the case may be. All right, pause the video, try the student problem. Okay, so again, we need the magnitude first. So the velocity, the vector is the square root of 4 squared plus negative 3 squared. So that's 16 plus 9, which is 25, which is 5. So therefore, the unit vector, the original vector is 5 long. So if I divide it by the 5, I'll get 1. So that's the original vector, 4i minus 3j. Divide that by 5. I get 4/5 I minus 3/5 j. So that is my unit vector. So it goes the same direction, it's just only length 1 now, which is handy because multiplying by 1 doesn't change anything. Alright, that is the end of part 2.